They'll want to see it slide.
Akan gitu sih. Kalau gitu jadi guna kelam, tapi ikan lain akan lagi saja bahasa Arab. Itu jadi kalau pakai kata ada. Kalau gitu jadi guna kelam, tapi ikan lain akan lagi saja bahasa Arab.
think we are good.
Okay, and the slides? How do I make the slides come up? Or he's going to do that?
He is going to go back and share the screen.
Okay.
Okay.
All right. Good morning from the American Center in Antananarivo, Madagascar. Okay. Good morning from the American Center in Antananarivo, Madagascar. We're joined here through the wonders of modern technology by Dr. Sun V. Nguyen, PhD, senior research scientist from the NASA Jet Propulsion Laboratory. And we realize it's well after 10 p.m. in California, in Pasadena, and we do thank you for joining us. Today we are taking part in the World Space Week celebration event, observing environmental changes from space, rural areas to megacities. And it's kind of a special day today because yesterday, you may be aware that we passed the world passed the threshold for the Paris Agreement for climate change coming into effect. That means 55 countries and 55% of the world's carbon emitters have formally ratified the agreement. That includes Madagascar on the 21st of September, and with yesterday's edition of the European Union, that now comes into effect. So it's a special day for saving the world from climate change. Thank you to today's panelist who will be joining us. He is Professor Charles Ratzi Faretana. He is Madagascar's World Space Week coordinator and a professor at the Observatory School. The program today is organized in collaboration with the Department of State's Office of Space and Advanced Technology in Washington, D.C., and NASA, the National Aeronautics and Space Administration. What is World Space Week? World Space Week is a United Nations celebration that takes place this week, October 4th through 10th, and which aims to educate people around the world about the benefits that they receive from space, encourage greater use of space for sustainable economic development, and to excite young people about science, technology, engineering, and math. And if you can see behind me, we've definitely excited a few hundred young people from Madagascar. We've exceeded the 200-seat capacity. We have probably 300, 350 people joining us in addition to our live audience. Science and technology are important in our everyday life, from the prevention of elimination of disease to growing food more effectively and keeping our environment clean in a world of over 7 billion people. And space can also help us combat climate change, which is what we're talking about today. And that's monitoring and measuring from satellites flying above the Earth to provide essential information on the effects of climate change on our planet. So thank you for joining us today. I'll now turn over the floor to Dr. Sun V. Nguyen from NASA in Pasadena, California.
Thank you, Tom, for the introduction, and greetings from Pasadena, California. I would like to welcome and thank you all for participating in this presentation. So let me start the presentation by saying that NASA has a fleet of satellites that observe the Earth. As you've heard, that NASA has a lot of mission to moons and Mars, but we do have a fleet of satellites for Earth observation. And in this presentation, we use some of those data that has been collected by NASA and by other space agencies from Europe and other places. So in this presentation, I will show how we observe the environmental change from space, from rural area into the megacity. First, I would like to acknowledge the contribution from my team, which has over 30 university, institution, and agency from 6 countries, including the United States, the United Kingdom, Italy, Germany, Belgium, and Czech Republic. And you see in this list a lot of names, but we're not going to go into detail. So the objective here is to detect and quantify the rural transformation so that we can investigate what caused the change, what are the impacts on the environment, agriculture, and multiple type of hazard. To do that, we have to have a new paradigm, and in this paradigm, what we need to do is, rather than look at a disparate array of individual city bounded by some artificially defined boundary in some area as a discontinuous collection of points in time. What we really do in the paradigm is to look at a continuum of time and space that span from the rural to urban area. So how do we do this? To do this, we need to invent a new method. It's called the dense sampling method, and it is patented. So the challenge here is that when you have a very high resolution image that collects from space, the area that you can see is really small. It's kind of like a postage stamp in some part of a city somewhere in the world. If you want to have a very large coverage, like 1,000, 2,000 kilometers in each swath, then the resolution is really coarse. You're talking about 25 to 30, even 50 kilometers, so that you can have a global coverage. So how do we resolve this challenge? And that is the key how we invent this method. So what we do here is that we pile up the frequent observation. In this case, I'm going to use a QuickScat satellite radar data. It collects global data almost 2 times everywhere across the world. However, the resolution is very low. So the method here is to pile up the image, and we sacrifice the temporal dimension to get the high resolution. The key is to decompose the target signal into 2 parts, the mean part and the fluctuating part. So I'm not going to go into the detail, but here what we try to do is go beyond the typical kind of resolution enhancement. You've heard of the CT scan in medical, where they pile up the image and reconstruct the high resolution image, for which Housefield and Cormack got the Nobel Prize in Medicine in 1979. And the heart of that is due to radon transform, and we need to go beyond that. So I'm not going to go in detail, but the point is, with this method, we can reconstruct the image at the scale of about 1 kilometer in the image posting. So with that, we can recreate the global image continuously in space with the global curvature and continuously in time during the time period from year 2000 to 2009, which is the lifetime of this NASA satellite called QuickScat. So once we've done that, the bottom line is that we can create what we call the dynamic atlas of a global continuum of land cover and land use change. This is fantastic in the sense that if you imagine you open your atlas and look at the world map, and that world map somehow changing in front of you from one year to another year. And that's what we are doing here. So with that, I am glad to announce that we already processed the data for all megacity across the world, defined as a city that contains 10 million people or more in terms of the population. But beyond that, we process the data not only for each city, but a continuum inside and outside the city too. So before we go in detail, let me explain to you what this radar or a signature in the image that you are seeing now means. So here we show the image over the Oklahoma City in US. So the red area in the middle is corresponding to the center of the city. As you go outside, it becomes yellow and more green. So the green represents the rural area. And if you pay attention, you see some of these dark color here and here and here, and a lot of those in the dark or grayish area, and those are actually individual building. But because this presentation image is coarse, you cannot see it from this. But I'm going to zoom in the next one, so you can see here those individual building. And the city of Oklahoma, not only that they have the building footprint on the surface, but they use a LiDAR, which is an aerial survey technique to measure the height of the building, which is represented by the color scale in here. And if you integrate them over the 1 kilometer pixel that I mentioned before, you know how much building volume within that 1 kilometer pixel. It depends on how many building you have there, how big the building are. So with that, we want to see the relationship between the radar image and the building volume. And here, if I put it in 3 dimensions, you can see the number 1, 2, 3, 4, 5, 6 here. Those are the building here, 1, 2, 3, 4, 5, which is a stadium, and 6 is this type of building there. So with that, we do a 2-dimensional correlation analysis to see how well the radar image would represent the building volume in the city. So we look at the west to east from south to north, and we look at the other way from south to north to west to east with many type of analysis based on the 2nd, 3rd, and 5th order. So the correlation is 0.52, the perfect correlation. If we can exactly accurately recreate the building volume, then this number should be 1. So we can do that to 0.85, which is fantastic because there are noises in the satellite measurement, and there are also noises in the aerial survey from the city of Oklahoma. So this demonstrates that the dense sampling method signature represent the building volume. And this is pretty easy to understand because if you remember, the radar was first developed to see the airplane coming in. If you see one airplane, you see a little dot on the screen, you see 2, you see more dot. And if you see many airplanes with a bigger airplane, then you see the screen would lit up. So similarly, if you have only one building in the area, you see a weak signature. If you see 2, you have more signature. If you see many buildings and many big building, you see a much stronger signature. So that's the idea behind this method, and it's really simple. So to give you a visual explanation, here what I show is the 3-dimensional image traced on the surface topography, and you can see the grayish, pinkish area is the center of the Los Angeles. And if you go further away, you go into the red area, which is the suburban. And if you go into the green area, which you can see in the mountain, which is the wilderness and the rural area. So to show that to you, I will put on here a 3-dimensional building for Los Angeles. See, you can see that in the middle part where the signature is strong, represented by the pinkish and grayish color, there's a lot of building. And if you go into the mountain, you become green because there's not too many houses in there. And we can overlay the road network, as you can see here. So now we know that we can recreate the calculation of the building volume. Then because we have the data from year 2000 to 2009 each and every year. So we can calculate the change of the number of building and the building size, so it contributes to total building. So we know the percentage of the building in each area of each city. So here as an example, I calculate the change in the building volume in a select sector of 14 cities along the San Gabriel Mountain. And I will explain to you why I look at the San Gabriel Mountain a little bit later. So you can see the building volume change can be a very little, like for example, Monrovia is only 1.7%, some other is 6 to 9 to 10%. But if you look at Etiwanda, it's almost like 45% increase. And by the way, JPL here is where I'm working. And it has a 6.5 increase in the building volume because we do build several new buildings in the decade of the 2000. And let me bring you again the attention to Etiwanda, which is having a very large increase in building. And here, if you zoom in using high resolution image, you can see this is the area that I calculate the almost 45% increase. This is for year 2000, so you see that there are houses here and here. But if you compare that with the 2009, you can see that there are a lot of new building in this area in the northern sector. And you can see here, there's a lot of new building and new building here. And there's some big building that built up in here too. So that represents about 44.7% increase in building volume. So why do we concern with this building here? The problem is that these cities sprawl into the wilderness, which is the mountainous area where you have some sort of trees and plants in there. For example, the city of Glendora, you see here, is sprawled toward the mountain. And in this image, what we show is the result from another NASA satellite called MODIS. And we can use this NASA satellite data to calculate how dry the vegetation is. If the vegetation is very dry, it's very dangerous and prone to a forest fire. And according to fire agency in California, if that moisture dropped to below 60%, they red flag warning that, and they call it critical danger. So those red areas that you see in this image are where the vegetation is really dry and it go below the critical threshold, which is very, very dangerous for Wi-Fi. And indeed, a fire occurred over here in January 2014. As you can see here, it started here, and then the fighter set up the perimeter within that they contain the fire and put it out. This image was sent to the fire agency in California before this fire occurred. The problem is that the fire department in California, they have to decide whether to keep renting the aircraft that drop the water on it or not. So after looking at this image, which show a lot of red area, they decide to keep that airplane. And lo and behold, when this fire occurred, they have the airplane ready to put out the fire. So this is one example of how satellite image can be useful to foresee the fire danger and get prepared for that. In the next one, what I'm showing here is the expansions of Saigon region. Saigon is in the South Vietnam, and this region contains the Ho Chi Minh City and other smaller cities around that. And the increase in terms of the expansion of the Saigon urban area from year 2000 to 2009, and you see in the movie, it's not 2, 3, 4, 5, 6, 7, 8, 9. So with that, we can calculate in terms of the lateral sprawling of the city quantitatively. And you can see here the result. The extent of the Saigon region in year 2000 is about 270 kilometers square, and in 2009 is over 1,000 kilometers square, which is equivalent to a quadruple expansion of the urban area in this Saigon region. Not only that, I explained to you that we can actually determine the building volume, which is the vertical build up in the third dimension. So if you look within the area of year 2000, and look at the same area for every year, which represents the center of the Saigon region urban area, then you can see that the building has been built up by more than 50% between the year 2000 to 2009, which is within the decade of the 2000. So beyond that, because we have the temporal data continuously in time and in space, for each given pixel, we can calculate the rate of change. And once you calculate the rate of change, you can identify where, in which part of the city where the build-up occur the fastest. And that would represent some sort of building hotspot. And in this example, you see this area here, which have a red area, which indicate a very large change in terms of the build up. And if you go further out, you can see it become less red, and then it's become orange, and it become green outside of the city. So this is because this area is developed as a new urban area called Hiệp Phước, and is a Cat-like port, which is now one of the biggest seaport in Vietnam, as you can see in this image here. So with this method, you can do this across the world, and for each city, you can see where these largest change occur and associate with that perhaps some sort of like a hotspot in terms of the development that you can identify. And we apply this method also to Beijing in China. So you can see here, what we plot in the gray area is the Beijing urban extent determined from our satellite measurement method. And on top of that, we plot the map of the administrative boundary of different part of Beijing. And you can see here from year 2000, is start to expand in 2001, 2, 3, 4, 5, 6, 7, 8, 9. And you can see from year 2000, within a decade, Beijing has expanding outward in a concentric manner to a very big extent. And that is equivalent to a quadruple increase in the Beijing side. Now you can see here, with the availability of the data every year, we can calculate the urban extent change from 1 year compared to previous year. So this is what we call the year-to-year urban change. So from year 2001, you have over 200 kilometers square of newly built area compared to year 2000. So between 2001 to 2004, you can see a very continuous increase in the urban expansion of Beijing. But then you look at 2005, what's going on here is suddenly reduced significantly, as you can see. It turns out that in year 2005, China's President Hu Jintao, he gained the power and he started to impose the policy to slow land confiscation, to reduce demolition, and to freeze urban industrial land conversion. And this is because of the mounting tension and the social discontent that he wanted to implement this policy in order to appease such a problem. But then if you look again in 2006, it go back to like before. If you connect all of these, is continuous, that linear trend as you see there. So this urban growth reduction policy is only a temporary measure. But then the year next to that, which is 2007, you see it not increasing as much, and because they delay the building so that they can get prepared to build much more in the Olympic year in 2008. So if you remember, the games of the Olympics was held in Beijing in 2008. And then after building a lot, they cannot build that much as before. So this example would show you how the satellite data can track the change in the urban as a consequence of differences in the policy implementation, to see whether such an implementation is temporary or it has a longer effect. In this case, we can see for 2005 that growth reduction policies is only a temporary measure. So from satellite, for this particular satellite, it's 800 kilometers in space. It's kind of amazing that you can see we can even track the consequence of urban change due to the policy change. And then the question that we look next, yes, so now we know where the city is, how it expanded, how is the rate of expansion would be, both in terms of the lateral and the vertical buildup. But if you think about that, buildings where people are, why do we build buildings? Because we live in it, we work in it, right? So it must be related to the population distribution. So what I show in here, there are a different data set for population. The Chrome data set is based on the census data. So it depends on which country. Some country carry out a census once every 10 years. Some other country would do it in perhaps one every 20 or 30 years, depending on the resources that they have to do this census data collection. The census data, one interesting thing about that is for many countries, or at least a number of countries, they record a person at the location where they live, which is your house, rather than where you work. And that is the essence of the Chrome data set. However, some argue that it's not a real representative of where people are, because you go to work, you go to university, you go to school, you go to market. Then, for example, if you go to work half a day and you stay home half a day, this data set called Landscan would assign half of you at the workplace and half of you at the home area, which is more representative of where you are on the average. The world population also using the similar kind of definition, which they call the ambient population rather than the census population. So it accounts both in daytime and nighttime where you are. And I will show you why this definition is important later on. Remember, where people are in daytime and nighttime can make a very big difference. Then we correlate this to see how well the satellite DSM data represent the population distribution. And this data set is only 0.65, and this technique for land scan is 0.71, and the technique for the world pop is 0.82. So it appears that the world pop model is the best one to represent the ambient population. If you cross-compare them, it's very hard to do because they do this data in each different year, so it's hard to cross-compare them. But because the satellite data has the data continuously in time, whichever year within that decade of 2000, you can compare them directly, and therefore you can evaluate all of these population data set by using the common denominator, which is the satellite observation. So now we know that the satellite data, not only it represents the man-made building structure, but also the population distribution from the center of the city go out toward the suburban and the outskirts and the rural area. So now that we know Beijing has been increasing, expanding by a factor of 4 in the decade of 2000. So what is the consequence of that? In here, what we show is the data from another satellite, which called the GOME satellite. This satellite can measure the nitrogen dioxide. Nitrogen dioxide is an air pollution chemical. It causes problems such like asthma. It makes you very hard to breathe, etc. So you can see here in year 2000, it's not too bad. The green means that you have a low value of these contamination from NO2. In year 2000, it's not too bad. 2002, you can see some there, but certainly in 2003, it increased a lot, and it increased strongly until 2009. So you can see here, increase, 2006, pretty bad, 2007, pretty bad, 2009, pretty bad. Whoa, what happened to 2008? You may already guess, it's the Olympic year. In the Olympic year, the government of China implement the policy trying to clean the air, and you can see here it worked. So if there is a will, there is a way. If you want to implement a policy to clean the air or to reduce the greenhouse gas, is doable. It just depends on whether there's a willingness to do that. So you can see here as one example. Then in 2009, it suddenly increased strongly back up, as you see there, and so is negate the result of the reduction of the to get the clean air in the Olympic year. So that's another example of a temporary policy. So once you have all of these data, what we can do further is to put these into the model. And this type of model we call the Gator GC-MOM. It's run at the Stanford University by Professor Jacobson from California. And it connects the climate scale into the urban scale. I'm not going to go into detail of this model, but it can account for all kinds of chemical in that. So then from here, we use the satellite data as input, and then we can calculate a various number of changes: the albedo change, soil moisture change, ground temperature, surface air temperature, surface relative humidity, 50-meter wind speed, surface ozone. Surface ozone is another pollutant, and aerosol, which is the dust in the air. But you can see each of these has some sort of ring around it. That is because the center of Beijing has been there for a long time. And when they start to build out, the area of the change is for the newly developed area, which are those rings. And it is in those rings that suffer the most impact. And then the conclusion is that within those areas of newly built in the urban expansion of Beijing, they suffer the increasing urban heat, the soil become drier, there's more air stagnation, there's a worse smog condition, there's a more ozone pollution, and there's more dust that mix up into the air. So that's the consequence of the urban development as an impact on the environment. So beyond Beijing, since this data set is global, we can look at really big area, and the area we look here is the central eastern China. And in here, you can recognize some of the cities, Shanghai here, Hangzhou here. And in this plot, what we show is the black area is the city extent in the year 2000. And the background color represent the rate of change of this area. So you can see the red color indicate a very large rate of change, and the blue indicates there's a little or no change. So this is in year 2000. Let's see what happened after 10 years in the decade of 2000. Wow, you see there, all the city has been developed so fast that it become connected to each other. You see here Shanghai, Suzhou, Nantong, Chengdu, and Nanjing, all connected. It become a phenomenon. For that, we call it the mega urban agglomeration. So it's not only isolated mega city anymore. It is the whole mega urban agglomeration that is connected to each other. And you can see here also Ningbo, Shaoxing, Hangzhou, and Jiangxi all connected together. So once this happened, then what could be the consequence? To illustrate that point, I show you this map. You can see here Beijing, which increased by a factor of 4, like in the previous view graph that I showed earlier. But if you compare that to the mega urban agglomeration in Shanghai, is several times even bigger than Beijing. And that would represent a challenge to the Westphalian system, in which each nation state sovereignty is only recognized by one power without the interference of the external factor. So to represent China, would it be Beijing or would it be Shanghai? As Shanghai mega urban agglomeration becomes so big, so large, which is strong in economic power, would come along with that, the political power. So what's going to happen? From here, we can even suggest some future scenario as a consequence. The first scenario is collaborative. So everybody get big, we work together, make everything work well, great. The second scenario could be hostile. They can fight each other. Then the third scenario could be competitive. Shanghai is big, Beijing want to be bigger. And that seems to be the case here because the government, the central government of China has approved the plan to build the Jingjiangji mega urban agglomeration, which would, in the end, has 130 million people, which is more than the total population of Japan put together in that one single city. So for that, you can imagine the tremendous problem in the communication, transportation, pollution, etc. This is another example where we have this rural to urban continuum, and this is in northern Italy. So you can see here, again, the red area represents the urban area. This is Milan, which is a big city, suave, Padua, and Venice, which is a big city here. And you see the green area, which is the eastern arms, the mountainous area, Upper Nile Range. The purpose of this investigation is to determine how the groundwater is contaminated. You can think about it, and it's very interesting in the sense that you cannot even see the water under the ground surface, let alone estimate how much chemical water pollution contained in that. Especially if you look from space. As I say, this satellite is 800 kilometers in space. Then how can you even do something about that? To explain that, actually the groundwater contamination, whether it's vulnerable to chemical contamination like nitrate, then there are two factors. The first factor is the natural factor, whether the water is deep or shallow, whether it's moving or it's just stagnant, and whether it's protected by the clay layer or not. But then if you say that an area has shallow water, is not really protected by a good layer of clay, but if there's nobody there to do any source of pollution, then it doesn't matter. It's still good water. There's no contamination. The second key factor for this is the anthropogenic factor, which is where humans are. Where we are, we have activity, we release bad stuff, we put out garbages, etc. So to estimate that factor, we would have to know where people are and where the city are being developed. There are different kinds of data set to do that. You can look at the population census data, which is not a very well representation because the population census put you at where you sleep, but where you go to work, you also release stuff, you also throw out garbages, right? So it's not really representative. The other data set is high resolution aerial survey, but because that very high resolution, each time you can look at one area in 1 year, in the next year you look at another different area. So there are big gap in time and in space. So the result is very noisy. It turns out that the satellite DSM method that we present earlier is the best one to assess the groundwater that is vulnerable to contaminant. And here we show the map of different level of vulnerability from 1 to 5. And then they do have well, which is they drill down to the soil and make a measurement to test to see whether these results make sense or not. And you can see here the frequency of contaminant increase clearly here as we go from class number 1, which is no contamination, to class number 5, which is the worst contamination. So this is verified the result. And you can see the cross-hatch area here is the area is defined as there is an increase in the urban change with a positive slope. So you can see it's consistent very well with where the higher class of water vulnerability is. So this is another example that why from space you can have some sort of assessment done to see where the water can be contaminated. And now you know the current condition of the contamination, you know the rate of change. You can use this kind of data to project into the future. 20 years from now, you ask yourself a question: if I don't do anything, if I let the status quo, let it changing as is, then what's going to happen? Or you can suggest that the government to impose a certain restriction, then you can estimate how better it can be. Or if the government let it loose and don't have any control, what worse it can be. So this is another example to look at the groundwater contamination. Now we can do this in even a bigger area. And here in this example, we just show two images. One is the intensity and one is the variability. To detect the city is have a higher backscatter, but because the building structure is have a larger variability in these azimuths. So by combine that, and we can look into each cities, where they are, how they expanded out, how they go into the rural area at this subcontinental scale. And we can do it at the global scale too. But here, I just showed the low resolution versions of these satellite image to show you that we have the capability of cover gigantic area. In this example, it is the Indian subcontinent. So if we have this kind of data, what can be useful? And for that, we can look at the problem of the vector-borne disease, such as malaria and Zika, over the entire Indian subcontinent. So using the satellite, we know where the city is, how it transitioned in the rural area, the population distribution in terms of the ambient population, which we know where in daytime and also in nighttime people are located. And then on top of it, if you use the population dynamic data, such as from the cell phone tracking, then you can see how people moving around. So with that, it is very important as a layer of data that is required to represent the rural, urban, and peri-urban area as a continuum of build-up density rather than binary, which is yes or no. You cannot say that yes city or no city, or yes rural or no rural, to determine whether the mosquito would come in or come out. There's no such a thing. So, but if you look here in terms of these two problems, the malaria is caused by the Anopheles mosquito, which is active at nighttime, whereas Zika is caused by the mosquito called Aedes aegypti, which is active in daytime. So it's better to know where the people are both in daytime and nighttime. So that would connect you to the idea that I explained earlier, why we need to know where people are in both daytime and nighttime. And with this kind of data, such an investigation can be done to see how these vector disease can potentially spread out in a different kind of urban area through the rural area, and how people are moving around, and how these disease can be spread out over the large scale, in this example, which is the subcontinental of India. Now, let me switch the gear to that. Now we already talked about large scale. How about high resolution? The satellite capability can do that also. And this example that we show for New York with a high resolution, this is the synthetic aperture radar by the European Space Agency, and which called the Sentinel-1A synthetic aperture radar. It's the same kind of thing, it's a radar. And you can see it have a different type of data with different polarization. So this is for the copolarization, and this is for the cross-polarization. And in this image, you can clearly see the area where the land is bare, such as cement without any building on top of it, like this airport, where you have the cement runway. You can see it here. You can detect those areas with the bare soil or bare surface, whether it's soil or cement. Then you can detect those areas. And it's important to detect those areas, because if you imagine where there is an area where people cut away all of the tree and leave the surface bare, which is the deforestation. So with this kind of measurement, you can determine where the deforestation occurred at the resolution of 20 meters, which is fantastic. So this is another example at the other end of the scale, which is very high resolution. Beyond that, we can also increase the information content from satellite data by combining with other data sets, such as the night light, which is a satellite measurement of how the light would occur at nighttime, and the combine between the radar and Landsat. And we developed another indicator, which we call the infrastructure index, which combines the NASA radar, which we call the SRTM, and Landsat data to identify the urban areas here. And this is an ongoing research, which will show the result in the future. So with that, in summary, we showed the DSM method that enable the observation of rural to urban transformation across a time and space continuum. We show that the satellite represent the physical building as well as population distribution. We look at the Saigon region, which expanding tremendously outward and upward. We show the Beijing that quadruple in term of the urban extend in the decade of the 2000 with excessive air pollution problem, the mega urban agglomeration, which caused the unbalanced development in different regions of a country. It may become a geopolitical hotspot from this extreme urbanization. We look at the northern Italy and determine how the groundwater can be contaminated. And we look at the Indian subcontinent to show how we can investigate the vector-borne disease such as malaria. So with that, I would like to conclude this presentation. If you have questions, you can ask me now, or you can contact me at this email address, and you can take a look at the website.
Oh, okay. All right. Thank you very much, Dr. Nguyen, for the presentation. At times when we hear about all of the challenges that we're facing in our modern world, it can be a bit frightening. But it's very comforting to know that people like you and other scientists are working on developing tools that can help us detect the change that is happening on our world, how quickly it's happening, and to help policymakers come up with different policies to try and address those things. I think that some of the tools that you suggested are very relevant for Madagascar, which, as you probably know, is suffering from deforestation at a huge scale, and there's a huge amount of biodiversity here that we're looking to protect. At this point, I would like to hand over the floor to our audience members, and I think I'll call him Dr. Charles, to make it a little bit easier to pronounce his last name. Dr. Charles Ratsifari Tana looks like he has the first question for you. Thank you very much.
Okay, thank you very much, Dr. Nguyen. I'm just blown away, the kind of information that we can get from this, from the satellite survey. It's just fantastic. Now, I'm thinking about the country of Madagascar. The way I say it, right now we have something like 2 million people in the city of Antananarivo, our capital city. And we already are experiencing some terrible traffic jam, and problem of sanitation, problem of all kinds of problems. Anyway, it's really, the way I see it, it's really a tragedy unfolding in front of our very eyes right now. And I think that everybody is aware that something really should be done. It's just that was just a quick comment that I made. But I have a small question. What is exactly the Westphalian system? And after that, I will just hand to the floor to ask the questions, because I'm sure that they have some.
Right. This is a question that I think the State Department can answer very well. So Tom, if you want to take this question, you feel free to do that. Otherwise, I can have a simple explanation. So
all right, I don't want to take over the presentation, but the Westphalian system is the system of states and nations that we have today, and how countries are run by governments. And what he was demonstrating was that when you have a mega urban agglomeration like what's happening in Shanghai, that threatens to upset the balance between nations, their capitals, and their leaderships. Just to make it brief.
Okay, good. Excellent.
Right. In the essence, that's what it is. Yes. Thank you, Tom.
Okay.
So I'll open the floor to other people in our audience that may have questions. Yourself briefly.
Thank you. My name is Rakutundena Suluforsu from the University of Antananarivo. I am a senior lecturer and research scientist. My field of research is remote sensing and digital image processing application. Thank you very much for your presentation. My question is about, do you have images of Madagascar? And if yes, how can obtain it? Thank you.
All right. I don't hear the question very clearly. However, let me repeat it to see whether it is the correct question that I hear. So your question is whether we have the images from Madagascar and where you can get it, correct?
That is correct.
All right. Yes, first of all, the NASA data policy is totally open and accessible. There is a data center that hold NASA data. If you can go to the website, you can even Google it, like the EOS disk to PODAC, etc. So the NASA data is free and accessible. And this is very important policy, and NASA has been doing these policies since the beginning. So all NASA satellite data for the Earth observation are free, and you can get it. It's just a matter where you find it. So you need to do a little bit homework to search for the kind of data that you want. Then follow with this policy. The great news is the European Space Agency now have the data policy that also open, free, and accessible. So you can go like the image that I showed for New York, 20-meter resolution, that kind of radar data is also free and accessible. So you can go to European Space Agency website and then do a little bit homework, then you can see where the data is located. And then you can download those data. And then, of course, once you have that data, it's in some sort of format. It can be in GeoTIFF, etc. So one of the things that we do here at the Jet Propulsion Laboratory, we do all the technical work, like how we calibrate this data, how we geolocate it, put the data at where it should be, accounting for the height of the land surface, like the digital terrain model. And then you can locate the data precise at where it is. And then we can even put it into some sort of data format, which is very easy for people to use. For example, the Google Earth KMZ. If you have the image in such a format and you have the free Google Earth, you can download, then you can double click on the image, and then it open up. If it Madagascar image, then you can see how Madagascar look like in that. And then if you follow my presentation, you can look at the cross polarization, and where you see the blue area, you know that area is either bare soil or it's an area that where the tree were cut off. Then you have this kind of data in time, so you can look at last year, this year, and in the future, if you have more data, you can pair the data between different years. Then you can see where the blue area occur, and you say that, aha, it was green before and now it's blue. Then you can know that, wow, this area is maybe some sort of deforestation going on. But to answer your question, yes, these data are open, free, and accessible.
All right, thank you. Any other questions? All right, and if you can't hear it, I can paraphrase the question again.
That'll be great.
I am Robson Jean-Jacques. I'm a lecturer at the University of Antananarivo. I want to ask about this method. It's not necessary to get the data from the field after getting data from this method from the space to find how you process the data.
Okay, I don't believe, I'm not sure we understand your question.
I want to say, if we get the data from the space, it's not necessary to get the data from the field, from the space, and to find how is it the precision of the data.
Okay. Yeah.
Okay, I think I've got it. So he's saying and correct me if I'm wrong. I'm gonna rephrase it a little bit. So if you get data from the satellites and then you get data on the ground, how do you make a comparison to ensure that the data you're getting from space is correct? Have I explained it correctly? Okay.
All right. Yes. So let me answer this. in this way. First of all, the radar signature is a engineering quantity. It's measured in dB, and normally the general public don't understand what dB means, what it represents. So to understand it, you need to know what the satellite data represent. In the case that I show here, that it represents the number of building, how big the building is, which is the building volume. And I use the example of the aircraft for you to understand it. So it is very important to have the science background in order to know exactly and scientifically how to interpret this data. So once you know that this data is responsive to the building volume, for example, in this particular case, then you can use the surface data as a verification and calibration of the data. For example, in the case of the Oklahoma City, that data set that they measure from the surface, where the building are, where the building footprint is, and how tall it is, this data set is very expensive and very hard to measure. So they can only do it in one part of the Oklahoma City for that 1 year, which was year 2006. Once you have that data, you use that to compare with the satellite data. You know that the satellite data corresponding to the building, but quantitatively how much it is, you use this data from the ground to quote unquote calibrate the satellite data. Once you know that, you use the satellite data to reconstruct for all Oklahoma City, not only for 2006, but from 2000 to 2009 throughout the entire decade of 2000. That is the strength of the satellite data. And once you know that, you can expand the same method to other cities across the world. Similarly, the population data, you need to know the population data for some year. Like, I don't know how often Madagascar carry out the census survey, probably once every 10 years or 15 or 20 years.
The last one was unfortunately 1993.
Right. So if you have one of the year, then you can calibrate that. Then you use satellite data to calculate for all the other years. So you can kind of equivalently have a quote unquote population data for each and every year. And not only that, you know where this population is distributed, whether the population is increased more in the center of the city, or there is more increase in the outskirts of the city, or maybe there's more people come into the city to increase the population in the city, like the migrant worker in a number of cities that go from the rural area to the urban area. So that's a very good question. It's a combination of satellite data with the ground truth or surface measurement. The beauty of the satellite data that is allow you to expand your observation with a large view from space that is a continuum in time and in space.
All right, thank you. Other questions from the audience? All right, we have one in the back. All right, thank you. Other questions from the audience?
Hello, my name is Panu Hattengawan and I'm a student at Alliance Française Ansabe. My question is, have you ever captured images that you were not allowed to show?
Did you hear that? Did you hear that?
No, I couldn't hear it. Can you?
So his question was, he's a university student here, and he wanted to know if you ever capture images on the satellite which you are not allowed to show.
First of all, the NASA satellite data, as I mentioned, we have a fleet of satellites from NASA that measure the Earth's surface across the world. The NASA data are totally unclassified. And as I say, the NASA data policy The data that collected by NASA satellite are totally open, free, and accessible. So if you see any data, you can show it anywhere you want from NASA. I mean, that's a different story from the Defense Department. They do have a satellite which is classified. For NASA, the data are not classified. And then we have many kind of data. And in this presentation, I just show you a really tip of the iceberg of the kind of data that NASA are collecting. And all of the NASA data are unclassified. And if you get the data, you can show it anywhere.
All right, thank you for clarifying. We have another question coming. It just takes a minute to get over there.
All right.
Hello. My name is Hans Champin. I'm a student of l'Agence Française. And my question is, how much does it cost to make a satellite?
So he's interested in the cost of a satellite.
All right. It's cover a really gigantic range of costs. It can be a function of what kind of satellite. There are some really small satellite, like CubeSat is just probably about the soccer ball size. Well, you play soccer over there, right? There are satellites that are that small, which is not that expensive. I don't know exactly the price for that, but there are satellites that are gigantic. It's like a bigger than a bus on the surface. Those are very costly, and it takes a lot of big launcher to launch it. So the total cost of that, not only just the launch, just to put the satellite over there, but to develop the satellite, to maintain it, to collect the data, to process the data. And for that kind of big, large satellite mission, it can cost as much as $500 million or $1 billion. Does that answer your question?
My name is Celia, and I'm from I'm a student from Alliance Française en Paris. I want to ask you, when you send people in the space, how many people do you send, and how long do they stay?
Okay, this question may fall outside your area of expertise, but this student is asking about how many
people do they stand in the space, and how long do they stay there?
Yeah, how typically when people are sent into space, how many people are typically sent, and how long do they typically spend there? And again, this is outside of your area of expertise.
Right, that is correct. NASA has many different directorates. One directorate is for the science directorate. Under the science directorate, there's a planetary and there's a earth science. So I belong to the earth science. And there is a manned space program, which is a different program. And I do not belong to that program, so I do not have the exact answer for your question.
All right, thank you very much, and we will. I think we started late, but we're getting to the point where it's an hour, and I know you want to get to. It's getting late in Pasadena, so if you don't mind, we'll just have one more question if someone has one, and then we'll bring.
Fine.
All right, thank you very much, and we will. Any more questions? Yeah.
I'm Erika from Polytechnic at Anna Maria. I'd like to ask you, with the researches that you have already done, do you believe in UFOs or IT?
So last question, she's asking, well, given all the research you've done, and again, this may fall outside your area of expertise, but maybe from talking to your colleagues, evidence for UFOs, evidence for plant life on other planets?
Right. That is another different program. You know, there are very large antenna dish from different area in the world that they try to measure some sort of very faint radio signal. And some of the radio signal may have a structure that can be attributed to an unnatural source. But again, Tom is correct. This area is belong to a different part of NASA and other agency that I'm not working on. So I cannot give you an exact answer to that question.
Okay, thank you very much. Thank you to our participants in the audience for coming out in such strong numbers to hear your presentation. Thank you to Dr. Charles. If you want to add anything.
No, it's okay.
No, feel free.
Thank you very much. I just want to thank you for this good presentation and for answering all those questions.
And we wish you the best of luck in continuing to work on some of the solutions for the problems that are facing us. Thank you.
Thank you for having me, and thank you all for participating in this event. I hope that you find the presentation useful, interesting. All right.
Thank you. Good night.
Good night from California.
Italy,